Hello, I'd like to welcome you to Lecture 19 of 3N03. We'll start in this lecture our discussion of binary numbers and logic. We'll talk about logic gates and synthesis of different logic functions. I will start in this lecture by just giving you some overview of very important things you may or may not have covered before for binary numbers. And we'll take it from there to discuss different type of gates and their implementation using diodes and using transistors and so on. We are more used to using decimal numbers in our calculations. Decimal numbers are based on powers of 10. For example, we have here something like this one, 562, and I do have a typo here because this is 562 to base 10. So I will usually indicate the base in the subscript as shown here. So this is 562 and this is base 10. So this means that 2 is multiplied by 10 to the power 0, 6 is multiplied by 10 to the power 1, 5 is multiplied by 10 to the power 2. So we multiply the value of every digit by powers of 10. And every digit can take a value between 0 and 9. So this is very similar to different other type of systems. I'm not going to talk about all of them, like the octal, using base 8 or using base 16. We'll focus mainly here on base 10 and base 2. The same thing will happen when we talk a binary number 110, and when it's base 2, and when it's a binary number, I will indicate it by a subscript 2. So for this one here, 110, it's base 2. This equal to 0 multiplied by 2 to the power 0, 1 multiplied by 2 to the power 1, and 1 multiplied by 2 to the power 2. And when you sum all this, of course, this will give you the decimal number 6. The same thing is happening for the first one. So we have seen binary numbers before during this course when we talked about digital to analog conversion and the analog to digital conversion. So a binary number 0000 is simply equal to decimal number 0. A binary number 1000, it has only 1 in the fourth digit, which is really multiplied by 2 to the power 3. This will give you 1 by 2 to the power 3 will give you 8. This one here is 1100, so you have 1 multiplied by 2 to the power 3 plus 1 multiplied by 2. Here I have this one 2 to the power 2. Of course, this one here has a typo. This one here is a 12, is not a 10. Okay, if it is 1, the one with 10 is 1010. This will be equivalent to 10 decimal. Okay, 10 base 10. Okay. And the last one I'm showing you here in these examples is this one here. All ones for these 4 digits equal to 15. So we'll now realize that if you have n bits, we call each one of these a bit. Each one of these digits, these binary digits, a bit. It can have a value of 0 or a value of 1. A value of 0 we really consider it to be, we call it logic 0. It can be 0 volts, or it can be any low voltage, or even a negative voltage. And we consider the value of 1 to be a high value, logic 1, or it can be an actual number. It can be 5 volts, or it can be 12 volts, depending on the circuit. So just remember that if you have an n bits, like here we have 4 bits here, these 4 bits can accommodate numbers, decimal numbers, from 0 up to 2 to the power n minus 1. So here n is equal to 4, so you can accommodate 2 to the power 4 minus 1, so you can go up from 0, 0, 0, 0 up to 1, 1, 1, 1, which is 15. This is a maximum number, this is a maximum decimal number that can be represented by 4 bits, 4 binary bits. Okay, so remember, we need if we are talking about bigger numbers, we need more number of bits. And we have computers that have 32 bits, we have computers that have 64 bits. So they store numbers in either 32 bits or 64 bits. So the more the number of bits available, the larger the numbers we can accommodate, or the higher the precision even in the calculations we can do using these binary numbers. Okay, I thought this would be an interesting fact to mention to some of you, that the person called the father of all of computers is actually a mechanical engineer. And his name is Charles Babbage. Maybe some of you can research this name. But in the 19th century, he invented the first computer, and it was a mechanical computer. And he used mechanical cranks and used decimal. It was base 10, not base 2. It wasn't a binary system. It was a decimal system. But this is really was the origin of all the computers that we know now right now. And Charles Babbage is called the father of all computers. Nowadays, modern computers use binary systems, not decimal systems anymore. They use them for summing numbers, subtracting them, multiplying them, dividing them. They use them for display. The display that you see on your screen is really represented by some numbers inside the corresponding memory, and so on. So binary numbers, as we agreed, if we have a binary word will consist of a number of bits. Every bit can take a value of 0, or it can take a value of 1. We call it logic 0 or logic 1. Low value or high value. And this will depends, of course, on the actual voltage corresponding to these values that is determined by the logic you are using. If you are using a diode, there may be some values you have to use. If you're using a MOSFET, other values, and so on. So inside our computers, you will see billions and billions of storage units. These are the bits we talked about. These bits assembled together in the form of words, and every word will have a meaning. It can represent the value of some variable. It can represent the intensity or the color of a pixel on your screen, and so on. So if you take a look at your computer, and maybe if they have some special eyeglasses with which you can see these electric signals, you'll see that the memory inside your computer is really made of billions of capacitors. And every capacitor is either charged or discharged. And when it is charged, it represents logic 1, which is a high value. When it is discharged, it does not have a charge, it represents logic 0 or a low value. Okay, and we use them, as I said, for carrying all type of data, doing all type of calculations, storing information, storing the display information for the screen, and so on. All computers communications are also done in a binary way. So you can see here, these computers can send a sequence at a time train of bits. This is 0, this is 1, 1, this is 0, this is 1, this is 0, 0, 1, and so on. So these bits sent from one computer to another and then received. Then of course they have certain handshake regulations or rules you have to follow, and so on. And of course sometimes they have to use modulation. They have to be modulated, so we can modulate them with high frequency signals in order to be able to send them, and so on. But in essence, all the information are being exchanged between computers and over the internet in the form of bits and sequences of bits. Okay, so this is really, binary numbers are really the essence of modern communication that we have right now, modern digital communication that we have between a computer and another computer, or over the internet, or whatever the case may be. Okay, so here we have some examples of binary numbers. We have seen similar one to this one. This is a decimal number 11. It's written as 1011, and this is using base 2. Okay, so this is 1 multiplied by 2 to the power 3, 1 multiplied by 2 to the power 1, plus 1 multiplied by 2 to the power 0. This will give you 11, and it's 11 base 10. You can as well represent fractional numbers. So this one here, this one, you can see this point here. This one will be multiplied by 2 to the minus 1. This 0 will be multiplied by 2 to the minus 2. This is 2 to the minus 3. This 2 to the minus 4. Very similar to what we do with decimal numbers. But decimal numbers are multiplied by 10 to the minus 1, 10 to the minus 2, and 10 to the minus 3. And this is how we can represent fractional numbers, or to base 10. This is exactly what we have here. So this number here, if you try to see it, it is 1. 1 multiplied by 2 to the power 0 is 1. This will give you 1/2. This will give you, this one here will give you 1 by 2 to the minus 1, so 1/2. this one 0 multiply, this 0 multiplied by 1/2 to the power 2 or 2 to the minus 2, so this is 0. This here 1 multiplied by 2 to the minus 3, 1/8. This is 1 multiplied by 2 to the minus 4, 1/16. So if you sum all these, you get 1.6875. Again, you can represent also complex numbers, and here this one here is really the base that we have. So these two here, maybe I can try to erase this one here. This one is really the base that we have. So this base 2. So the number is minus 1.00.1, and this is base to base 2. I must have a way of storing this sign. So maybe we can represent it by an extra bit. Then maybe an extra bit. If this bit is 1, then this is a negative number. If it is 0, then it's a positive number. And the rest will follow exactly the same thing. This is 1 multiplied by 2 to the power 2, 0 multiplied by 2 to the power 1, 0 multiplied by 2 to the power 0, plus 1 multiplied by 2 to the minus 1. Okay, so we can get this number here. This will give us, of course, I have another typo here. This is really 1 multiplied by 2 to the minus 1. So this will give you half plus 4 will give you 4.5 with a negative sign. Okay. Adding binary numbers, we add them in the same way we add decimal numbers. And I have here a statement that I noticed when I was taking a look at this lecture, it wasn't written properly. When we sum two decimal numbers, say maybe 30, okay, let me try to have that. And when I sum 35, say plus 68, okay, we say we first sum 5 plus 8, this will give us 13. So we put 3 here, and then we carry over 1. This one really is 1 multiplied by 10 to the power 1. So this is really 10 to the power 1, okay? And then we sum it, we add this 1 that we have here to plus 3 plus 6. So this will give me here 0. So I can type here, I put here 0, and then I carry another 1, and this one is really 10 to the power 2. So what we have here, our result will always be digits between 0 and 9, but we carry over multiple powers of 10. Okay, so this is not really properly stated here. The digit, the number that we get, the digits are always between 0 and 9, but the carryover are always multiple orders of 10, 10 to the power 1 or 10 to the power 2 and so on. So either when we sum two digits, either there is no carryover or there is a carryover of 1 which moves to the next digit, and this one is effectively either 10 to the power 1 or 10 to the power 2 or 10 to the power 3, depending on what digit we are summing. The same thing happens for binary numbers. When we sum two binary numbers, we sum them, and the result for every digit will be either 0 or 1, and then we can carry over always multiple powers of 2. So when I carry over 1 from here to here, this is 1 multiplied by 2 to the power 2. When I carry 1 from here to here, this is 1 multiplied by 2 to the power 3. So the carryover is 1. We write it as 1 in the same way we write it here, but has a different meaning. Here it's powers of 2, while here it's powers of 10. Okay. For example, let's look at this example, which I borrowed it from one of the references. So if you have here 1 plus 0 will give us 1. 1 plus 1. Okay, 1 plus 1, this is 2, but I cannot represent 2 in a single digit. So I write 0, and then I carry over this 1 there. 1 plus 1 plus 1, this will give me 3. Then I put 1 here, and then I carry another 1, which represents really 2. And then 1 plus 0 plus 1, this will give me 2. But I cannot really represent 2 in a single digit. So I put here 0, and then I carry 1 to the next digit. So my answer will be 10101. Okay, so the sum of these two numbers is this one. And you notice here we have an overflow. What do I mean by an overflow? We sum two numbers that were represented by four bits, but the result turned out to be a number that required 5 bits. Okay, and this can happen sometimes when we have a program and we are using maybe 16 bits to represent a certain number, but the number goes higher than the value that can be represented by 16 bits. This will cause an overflow error. Okay, so let's keep that in mind, that in this case we sum them in the same way we do for decimal numbers, but when we carry over 1 from one digit to another, this is simply powers of 2. So here I'm carrying, this is 2 to the power 2, and this one here is 2 to the power 3. I'm carrying it to the next digit. So exactly what we do here, but the meaning is different. Now for addition of decimal numbers, very simple. When you add something like 316 plus 59, it's pretty straightforward. We know how to do that. You say, well, this is 5. I can carry 1 to the next digit. This will give me 7, and then I have 3. So the sum of these two is 375. Now when I subtract them, when I subtract 59 from 316, I simply have here to this 6, we cannot take 9 out of 6, so I borrow 10, it becomes 16, and this here gives me 7, okay? Then we have here 30, 30 minus 5, this will give us 25. So the answer will be 257, okay? When I subtract something like this, 316 minus 905, the answer is going to be negative, correct? So we can subtract this one, you can say this one minus this one with a negative sign. So if you do that, this will give you here 9, okay, 15 minus 15 minus 6 will give you 9, and then you can continue your subtraction operation. This becomes here 89, and this becomes 316, and then you can get your answer for this one. You can get 589 here for this one. Okay, please double check this. I'm doing it as I go. I may have a mistake here or there. Anyway, so this approach of subtracting numbers in decimal numbers is not very convenient for computers. And the easiest way and the way to do it in a computer is that they convert subtraction into addition. We have to convert subtraction into addition, and the way for doing that is to use something called complements. I will show you how this can be done for one example in decimal numbers, and then we move that to the case of binary numbers. For example, when I subtract, I can subtract, of course, here 355 minus 316. We can subtract that, becomes 39. Just to have a correction here, this of course is a negative answer. I forgot to add the negative answer of this one. 316 minus 905 becomes a negative number. I simply subtracted the second minus the first, but I forgot to add the negative number. Anyway, let's go back to this example here. I subtract 355 minus 316. If you do subtraction, of course 39, but I'm going to be doing it a little bit different way. I'm here using 3 digits for this one and for this one. Then I'm going to be using the tens complement, and to use something called tens complement means I will convert this 316 into the corresponding tens complement for 3 digits. So here I will have to get this equivalent number, which is 684. What is this 684? It's 1000 minus 316. It's 1000 minus 316. This 1000 is really 10 to the power 3. Because I have here 3 digits. So I created what I call here tens complement of 316. So 684 is the tens complement of 316 if we are considering only 3 digits. So now I go back and I sum 684 to 355. So I'm not going to do any subtraction. I created this here through some rule. It doesn't have to be through subtraction here. But I created this tens complement for 316, and it turned out to be 684. Now let's go back and add 684 to 355. If you do this addition, you'll see that the answer 5 plus 4 is 9. 5 plus 8 will give you 3, and then you carry 1. 6 plus 3 will give you 9, and then you have 10. So the answer, the first 3 digits will give you also the 039. It is the same answer here, but you have this carry over here, and this carry over is 1, meaning that your answer is positive. Okay, so let me try to explain again what I did here. We're not going to be doing any subtraction. Instead of subtracting 355 minus 316, we will add 355 to the tens complement of 316, which is 684. and then we'll keep only the first n digits. If I have a carryover, then the answer is positive. If I don't have the carryover, then the answer is negative. This is called tens complement. Okay, and the same thing can be done exactly for binary numbers. We can talk about the two's complement. Two's complement means try to find the complement relative to powers of 2. Okay, so now let's see the next slide, how we can generalize this concept to the case of binary numbers. Okay, so we have here this number which is 1001. It's simply equal to 9 decimal, and I would like to find its two's complement. So what you have to do, you have to create here this 1, 2, 3, 4. We have to create 2 to the power 4, and 2 to the power 4 is simply 1, 0, 0, 0, 0. This is 2 to the power 4, it's 16. Okay, it cannot be represented by only 4 digits, that is by 5 digits. And then I will subtract from this 16, this 9 here that I have. So 1, 0, 0, 0, 0 minus 1, 0, 0, 1. Of course, I'll end up with 7. 0, 1, 1, 1. So this one here is the two's complement of 1, 0, 0, 1. How did I created it? I simply, in the same way I did with decimal numbers, I created 2 to the power of the number of bits. I have here 4 bits. So I create 2 to the power of 4, so 16. It can be represented by 5 bits here. And then I subtract them, I got this one. So this number here is really what I should be using if I subtract this one here from any other number. Now let's do another experiment in getting the two's complement. I want to get the two's complement of this number here. It's a bigger number, 1, 0, 0, 1, 0, 0. So I have here 1, 2, 3, 4, 5, 6. I have 6 bits. Then I have to subtract this number from 2 to the power 6. 2 to the power 6 is represented by 7 bits. 1, 2, 3, 4, 5, 6, 7. When you do this subtraction, and you can do this subtraction, you end up with this one. Okay? Now, notice something very interesting about the two's complement. In order to get the two's complement, I do not really have to do any subtraction. I simply toggle the bits. So every 1 becomes 0 and every 0 becomes 1. And then I add 1 to that. For example, let's take a look at this one here. I want to find the two's complement of 1, 0, 0, 1. First step is make every 0, 1 and every 1, 0. So this becomes 0, 1, 1, 0. And then add to that 1. If I add to that 1, I end up getting 0, 1, 1, 1, which is exactly the same answer I got here. Okay, now let's try to find the two's complement of this number. We'll follow exactly the same procedure. I have 1, 0, 0, 1, 0, 0. Let's toggle every 0, make it 1, and every 1 make it 0. Then this becomes 0, 1, 1, 0, 1, 1. Let's add 1 to that. If you add 1 to that, you will add it here. So 1 plus 1 will give you 0. And you carry 1. 1 plus 1 will give you 0, and then you carry 1. Then you end up with this number here. 0, 1, 1, 1, 0, 0, which is exactly the same answer we got here. So what I'm trying to say is finding the two's complement does not require really a subtraction. It can be done in an automated way. Simply toggle every 0, every logic 0, make it logic 1, and every logic 1 make it logic 0, and then add 1 to the least significant bit. And so we tried this in these two. And by doing that, now we can do subtraction of binary numbers in the same way we did it using the tens complement. First, find the two's complement, and then add, and don't do any subtraction. So I'm showing you here an example. I would like to subtract 316 minus 59. 316, you can verify, is given by this number here. Okay, it's given by this number here. 59 is given by this number here. Okay, and both of them are using 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 bits. So first we find the two's complement of this one. I'm not going to be doing any subtraction. I will turn every 0 into 1, and then I will add 1. If you do that, this will be your two's complement. Okay, so instead of subtracting this binary number minus this one, I will add this binary number to this two's complement. And this is what I do here. So I'm now adding 316 to the 2's complement of 59. It has a value, of course. I don't know what this value, and I don't care. Now, if I do the addition, you do the addition the same way we learned. 1 plus 0 will give me 1. 0 plus 0 will give me 0. 1 plus 1 will give me 0, and then I will carry 1. And then you end up carrying 1, 1, and so on. You end up with this answer here. And there is one overflow bit. Okay? So here 1, 2, 3, 4, 5, 6, 7, 8, 9. You have your 9 bits, but you have 1. This one here is telling me that the answer is positive. If you try to find the value of these bits, you find here that you have, this is 2 to the power 8 plus 1. 2 to the power 8 plus 1 is simply 2 to the power, it is 256 plus 1 is 257. So we got the right answer. 316 minus 59 is indeed 257. Okay, so this is a great thing about this one. I don't really have to do subtraction. I can simply convert it to addition. The same thing happens here. If I want to subtract 316 minus 5905, this is a binary representation of 316. Okay, and I used here this number of bits that I have to make them. I think I used here 10 bits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is fine. The 2's complement of this number can be found very easily. Toggle every 1, make it 0, and every 0 make it 1, and then add 1. You'll find that this is the 2's complement of this number. So the 2's complement of this one is this one here. Now, instead of subtracting 316 minus 905, we will add 316 to the 2's complement of 905, which is this one here. So this is what we did here. Now let's do the addition. Again, 0 plus 1. 0 plus 1 will give me 1. 1 plus 0 will give me 1. 1 plus 1 will give me 0, and then we carry 1, and so on. So if you do that, you end up with this answer. And this answer has a 0, carry over, no carry over, okay? So this is telling us that the answer is negative. And the answer is negative. And then when you try to take a look at the answer that we have, which is the one that we have here, okay, you will see that this is really equivalent to 589, okay? So we know that the no carry means that the answer is negative, and you take a value of the number that you have, you will see that indeed 589 here in this case, okay? Utility of binary numbers. We use binary numbers to represent every digit. If you have on the screen, you see the character 1. This character 1 means that there is a certain byte written in the memory of your display. So every character we can display on the screen corresponds to a certain code. It's simply a binary code. So for example, this one 1111. If you have 1100, then this becomes this symbol here, and so on. So you have all these symbols, you have tables, you can look up these tables. We use binary numbers also for calculations, all type of additions, subtractions, multiplications, and of course the more number of bits we have, the higher the decimal numbers we can represent. If you have only 8 bits, 3 bits, you can represent only up to 8. If you have 16 bits, you can represent only up to 65,000. If you have 23 bits, you can represent up to 8 million in one word. So this telling us you can really represent all these you can use them to represent numbers inside your computer. Now we move to the second part, which is logical variables and logical operator. A logical variable, it takes two values, either true or false. For example, if I say the sun, it is a morning, it's still morning. This is either true or false. So this it is morning is a variable. It can assume two values, either it's true or false. True is logic 1. True is what we call logic 1. False is what we call logic 0. Logic variables were shown by a scientist called Boole, I think his name is Charles Boole, in the 18th century to follow mathematical rules, to have their own algebra. And these algebra are given by different operators, and operator, or operator, and so on. And operator means if you add two logical variables, then the AND will be true only if these two variables are true. So when we say it is morning and it is 8 o'clock in the morning, so I'm now ANDing two variables. If these two statements are true, then their AND is true. This is the only way to make the AND to be true. So both of them has to be true. Or means that either one of the two logic variables is true. So when I say X or Y, we usually represent the AND by a dot product and represent the OR by a plus sign. So when I say X plus Y, I mean if these two are two logic variables, that this is X or Y. Means that either X, for this to be true, this statement to be true, either X is true or Y is true or both are true. We have three cases here for the OR statement to be true. The not operator, it inverts a logic statement. So when I say it is not morning, if it is not morning, means that if this statement it's not morning is false if it is indeed morning. So for example, if a variable X is true, then it's not will be false. And if the variable X is false, it's not will be true. Okay, so the not operator usually represented by a prime or represented by a bar is true, or if the original variable is false, or if it is false if the original variable is true. So these are three basic operators that we use very often in logical operations. We have one of the gates. This is the AND gate. We'll see this one very often later in the course. We have here two inputs. These two can be, you looked at them as two logic variables, or we can look at them as two signals. These two signals can be either true, means I have logic 1 or 5 volts, or can be false, they are logic 0 or 0 volts, or depending on whatever the voltage may be. But the output Q from this AND gate will be true only if these two are true. So this we can form now what's called the truth table. And the truth table tells you all the possible outputs of your gate given all the possible inputs. For example here, if A is false and B is false, then the output will be false. Because the AND will be true only if these two are true. If A is false but B is true, then their AND is also false. If A is true but B is false, then their AND is also false. The only way to get both to be true is that A is true and B is true. So this is called the truth table. And again, I would like you to take a look to imagine that A and B can be either logical variables or they can be signals. And these signals can assume logic 1 means I have high value, 5 volts or 12 volts, whatever the case may be, or they can assume logic 0, which is low value. It can be 0 volts, can be -5, or the case may be. Okay, so remember this AND gate is extremely important. We're going to be using it over and over again during the digital part and in the rest of this course. Another important gate we care about is the OR. This is a symbol for the OR. It's a 2D OR. The output will be true if any one of these is true. When I say that Q is A or B, means that Q will be true if A or B are true. So this is the truth table. If both of them are false, the output is false. If only B is true, the output is true. If only A is true, the output is true. If both of them are true, the output is true. And again, I say true, but for signals, it can represent logic 1 or high voltage. The not means you apply a logical variable and the output is the inverse of this variable. If this variable is true, then the output is false. If this variable is false, then the output is true, as given by this truth table. And again, this means that if I put a high signal here at the input of 5 volts, the output will be logic 0, which is 0 volts, say. And if I put here a low signal, low input, or logic 0 at the input, the output will be logic 1 or high signal. Okay, let's take a look at this example. We'd like to find the logical expression represented by this circuit. So this circuit has 4 logic inputs, A, B, C, and D. we have two AND gates connected to an OR gate. Okay, and we'd like to find the corresponding truth table for this one. Of course, the output from the AND here, the output here is A and B. The output from here is C and D. And so F will be the ORing of these two signals. So F is equal to A and B or C and D. This is really the expression given by this function. And you can try to find the logical table of this function. So as I said, the output from here is AB, the output from here is CD, and the total output from this logic circuit is simply F1 or F2, and remember the OR represented by a plus sign while the AND by a dot. So this is the output. It's A and B or C and D. The output here will be, the output F will be true only if the output F1 is true or the output F2 is true or both of them are true. Okay, so now we can start to build the truth table, 4 inputs and 1 output, and then try to see how we can get true output for this function. So I plotted the truth table and I showed one part of it here to the left and the other part to the right. These are the 4 inputs and this is the output F. You can see every time when C and D are both true, then the output from the AND gate is true, then F will be true. So this happens here and this happens here. Every time when A and B are true, then the output from AND gate will be true and then F will be true. So this is why for these 4 we have true output. Okay, here we have C and D are also true. So out of the possible 16 inputs, I have 16 cases here. I have 1, 2, 3, 4, 5, 6, 7. 7 cases that can give me high output or true output for this logic function. And by the way, this concept of using AND gates followed by OR gates is used for something called programmable logic arrays. Programmable logic arrays can implement any logical function, as I will show you later. But this concept of using AND gates followed by OR gates is very widely used in logic design.